So basically, when we have a look at a rig, doesn't matter of onshore or offshore, we have a lot of parts, a lot of metallic parts, and also a lot of elastomeric parts, which are capable or which are used in this field. When you think of blowout preventers have a lot of elastomeric parts as well inside. When you think of O-rings or elastomeric rings, when you think of hoses, of liners, flexible, therefore also elastomeric materials. And also when we think of other waves of other Christmas trees here, for example, where also a lot of sealing has to be done to prevent the gas to come out of the whole stuff. When we now think what's happening to the material, rapid gas decompression. We have a defined temperature, for example here 90 degrees C, this only geometric picture. And then we are going to pressure up, for example here, very low pressure until 150 bars, with a defined media, for example carbon dioxide. Then at the beginning we have our elastomeric material, nothing will happen. When we split then to the compression phase, so we increase the pressure, we will have a short volume increase up to 10-20% of the material. Nothing else will happen in this compression phase. The problem is the phase after this compression phase, the depressurization or the decompression phase. So when we release the pressure, what we have applied to the material, then the material will increase one more time the volume, and this will lead to blistering, crack initiation, crack growth, and finally failure of the material. And to describe this, we have nascent nozzle testing standards. Nascent nozzle testing standards use such components, the next slide, with a defined temperature, with a defined pressure, gases, and also time and depressurization rates. After we have applied this elastomeric material to the autoclave test or to the pressurization test, we will cut the material in 4 pieces, and then we will rate the cross-section concerning the NORSOC, in this case the NORSOC testing standard, the rating matrix, and then we will see under the microscope such pictures where we have cracks, and then we have also ranking from 0 to 5. However, we did not know what happened with the material. We only see the fracture after we have put the material to the autoclave, and we have no idea what's happening during pressurization, during depressurization. And therefore, our scientific contribution or our way was to put an autoclave test system or to equip an autoclave test system with a camera system to see directly what's happening during the compression and during the depressurization. Due to the equipment with the window here and the camera, we can see the volume increase inline and can then basically on the cylindrical geometry of this volume of the specimen calculate the volume increase. And when we now go back to the first slide, we see here the temperature, the pressure, and the volume increase of the material. And what's happening at the beginning in the compression phase is that we have a short volume increase until we have established saturation conditions. We see here this gap is around, for this material, 6,000 to 8,000 seconds, and then we've reached equilibrium, and then the material stays constant, so the volume increase of the material stays constant. It means that we have a defined amount of gas, depending on the pressure, depending on the temperature, in the material, and everything is fine here. Then we start to depress the whole system, and when we depress the whole system, we see here that we have a short initial time, and then we will rise up to a maximum volume increase, in this case of up to 50%, and then material fades or it will resist this depressurization cycle. When you just can click on this picture, it's a video file. Yes. So the first cycle, the compression cycle, you see nearly nothing because it's very, very short volume increase. We have here 2 specimens. Now we have the depressurization. We have only changed the filler of the material. All other things are the same. And what we see here is that we have now the volume increase. And the left side We have here spontaneous crack initiation, and the crack grows until the surface of the material, and therefore the high pressure gas in the middle of the material can rapid or explosive go outside of the material, and therefore the material is blown away outside of this camera window. Afterwards, we've also cutted the specimens, and we see for the first material here the crack, which is going out through the complete cross-section of the material, and here we have no crack observed with the second filter. For the comparison of the different influencing parameters on this material performance, we used the volume increase during compression, the volume increase during decompression, and also the initial time until this volume increase happens. Due to the limited amount of time, I will only focus here to the influence of pressure, influence of depressurization rate, and the influence of gas, as well as influence of temperature as described in the paper. When we look at typical curves, what we have observed during the measurements, we see here for the compression phase and the increase of pressure that with increasing pressure, with 50 bars, 100 bars, 150 bars, the volume rises. We see a same tendency during the depressurization phase, and this was also a result what we have obtained, because when we rise the pressure, also the volume should rise, because the gas concentration rises due to the increasing saturation pressure. We've seen the same tendency, as I mentioned, for the depressurization, because when we have more gas in the material can increase higher the volume during the depressurization. And we've also correlated these results then with, on the left side you see the results for cylindrical specimens, on the right side you see the results for NORSOC testing standard. Then we went on to the influence of the depressurization rate, and we see that when we depressurize the material with 20 bars per minute or with 100 bars per minute, we see a strong difference. We see a volume increase from 20 to 30% for depressurization of 20 bars per minute. With 100 bars per minute, we see 45 to 55 volume increase during depressurization. Moreover, we also observed a strong influence on the dynamics or on the initial time. It means that the whole kinetics, how the volume change changes during or regarding this increase of the decompression rate. This means when we also look here at the results of the NORSOC ranking, because for the NORSOC ranking we did not obtain or did not see any differences, that we cannot correlate easily these volume changes to the NORSOC ranking were for the material. And this brings up the question if the NORSOC ranking is sensitive enough for material characterization in this field, and also to see to assist a future material development process. This rating or this the knowledge of a volume increase during pressurization and during depressurization is very important. To come to an end, we've seen that we have a clear influence of the volume observed or measured during compression and during decompression phase, for both for the rising decompression rate as well as for the increased amount of dissolved gas in the material due to the higher pressurization of the material. However, we've seen also that we have no clear connection to the NORSOC material ranking in terms of the higher decompression rate, and therefore we cannot easily correlate both material characterization techniques. Thank you very much for your